Hello guys. Hope everything is going well for you.
Good afternoon.
Hi. Okay, someone has a question regarding long kappa. Yeah, you can ask. What do you want to ask regarding long kappa? Yeah, I believe that. Why there are questions that are out of topic? You mean not related to mechanics so far? Yeah, we will have. I understand. So chapters which are kind of ahead from where you're supposed to be. That's a good question. I guess we will have on Thursday evening meeting with other professors who deliver this course. Let us try to discuss this question in more detail, so they will try to pick up problems which fit more or less better to what is currently going on. Maybe it's not so easy to do because if it's a problem which involves multiple steps, then it's very difficult to find yeah, I mean, obviously it's necessary to solve whole problem, not parts of it. But let's see, definitely this should be discussed during this meeting. Okay, topics of problems. Good, then maybe on Friday I can provide you some feedback on this question. Let's see how it goes. I agree it should be more or less related to these topics which are currently going. But I mean, if it's not well, so first of all, maybe I would just finish this question. So if it's not so far away, if it's really like some work done or maybe some momentum, you can just look it up maybe in the textbook. So in order not to lose points, because I believe it will not be like thermodynamics. So for sure it's like very far topic, which is not related to what we are doing now. But I will definitely ask those who are responsible for picking up problems to pick them up as much close to the current topics as possible. But if it's a little bit deviation, then I believe you can also try to look it up a bit. But let's first discuss this question on this meeting, and then I will provide you more information a bit later. So there is a question about midterm. Midterm will be, I believe, this Saturday. Just double check in the manual, it's written there. There is a table. Yeah, it is scheduled on Saturdays, all midterms, and probably, I'm not sure about final exam. Probably we don't have still a date for that. Not yet. So on Thursday evening, we will discuss. So we will have this meeting regarding Physics 161, and we will discuss the option to drop the lowest grade of homework assignments. We'll see if people agree with that. I will let you know, hopefully on Friday. So I figure out that a bunch of students didn't submit their homework assignment, like about 10 students. So I send email to them, and if there is a chance that among you guys there is someone who didn't submit it, please do it, because it's important part of your final grade homework assignments, and that is your responsibility to submit answers in time and in an appropriate format, so the long kappa software accepts it. We don't have technical capabilities to give you a chance for redoing this, and that's why you need to be very responsible on this part of your work. Okay. So I guess let us change the camera and continue our discussion. Just to remind you, last time we were talking about some friction forces, like stationary friction and kinetic friction, also some drag friction in friction of environment with respect to moving body. So let us consider now a number of interesting cases which can be useful for a better understanding of this topic. So first of all, let us consider a case when we want to figure out at which maximum angle we can tilt the plane on which our body is located. So it starts moving, taking into account static friction. Okay, then let's have some drawing. This is our inclined plane. Here we have somebody. This is mg. Then this is, here we have reaction of the plane n. So this angle is, let's call it theta. This one is also theta. We discussed this last time. And now we have some projection of this weight to x-axis and y-axis. So let's maybe show it like this. So here we have, it will be mg multiplied cosinus theta. And here we have mg sinus theta. Okay, and also we have now additional force, which is static friction force. Good. So our question now is how to determine the maximum angle theta of this inclined plane, at which our body starts to move down hills. So for this case, we need to consider like two forces, which are along the axis x. So it's mg sinus theta. It's kind of driving force which pulls our body down hills. And this stationary friction force. So this will start moving down hills when these two forces are equal. So they will compensate each other. So we know that stationary friction force is equal to the applied force and opposite in the direction. However, it reaches certain maximum, and this, like let's call it maximum value. And this maximum value of stationary friction force is mu s multiply n, where n is the reaction of the plane of this force. Okay, so this is the condition when these two forces are equal to each other, this body will start sliding down. So now we need to substitute n with its value, which is defined by the mg. So we know that n is equal mg cosine theta. And now let's write the final equation. We have mg sinus theta equal to mu s multiply, which is the coefficient of this stationary friction, multiply mg cosine theta. So we can cancel out product of mg, and we see that sinus theta divided by cosinus theta, which is equal to tangent theta, is equal to mu s. So this is the angle, tangent of angle theta. This angle at which the body will start sliding down is totally determined only by the coefficient of static friction, and that is the way how you can determine this coefficient. So you just put this body which has certain surface condition, like surface treatment condition, on a plane with the same or different surface treatment condition. So for particular surface, two surfaces conditions, you will determine this coefficient mu once you start to increase, like tilt more and more this plane and measure the angle at which this body starts to move down, like slide over along this surface. So tangents of this angle theta will be equal to your friction coefficient mu s. So this is the simple way how you can measure this friction coefficient for a specific body and plane. I mean specific treatment of their surfaces, because if you polish surface of the body and of the plane, make it very smooth, so of course this angle will be smaller, and the smaller mu, the smaller angle. So it will start sliding at a smaller angle because you need less driving force to pull it down.
Excuse me, Professor.
Yes.
So if the problem says that our body is sliding down, does it mean that our body will have like constant velocity with zero acceleration?
Yeah, I mean, if it's not mention that it has certain acceleration. It just tells that it slides down. It should be constant velocity.
So that is why in x-axis we take into account that mg sine theta is equal to fs max.
Yeah, that's when we have equal, let's call this mg sine theta driving force. So driving force is equal to the static friction force. So they compensate each other. It is sliding down, but there is no acceleration.
Okay, thank you.
Mm-hmm. You're welcome. Okay, let's go to another. So we already had a bunch of these examples with inclined plane. I guess it's time to go to a bit another class of cases. Let us consider some circular motion and like second law of Newton's law in the framework of circular motion. So let us consider some body which is attached to a thread, like some rope, which cannot be stretched, so it's unstretchable rope, and with its mass in comparison to the mass of the body we can neglect also. And let's consider a case when this body attached to this rope is rotating. So this is kind of circular trajectory, rotating around like above this axis. Let's call it O prime. So what do we have here? For instance, we would like to know what will be angle, let's call it alpha, if we know angular velocity of this uniform circular motion of the body. Then we know the length of this rope, and we know the mass of the body. So let's say we have this mg, the weight of the body. Then we have here some tension in the rope, which compensates the weight of the body, plus we have also this like centrifugal force, which is directed opposite to the radial acceleration. So it's we know that acceleration, like radial acceleration of uniform circular motion, is directed along the radius to the center of the circle, and it's equal to the, so this is our radius, and it's equal to omega square multiply radius. So that's why this like centrifugal force will be mass multiply omega square radius. So what we see here, let's maybe draw these forces separately. So because our image is already quite crowded. This body doesn't move in the plane of the image. So it doesn't move down or up, left or right. That's why like vector sum of these forces, omega square r, m, g, and t is equal to 0. That's why T, the tension in the rope, can be represented as sum of these two forces. So this is like minus T vector. And here we, from taking into account this condition of equilibrium in the plane of the image, we can write an expression for, first of all, for the vertical component and horizontal component. So it will be mg equal to T multiply cosinus theta. So we see that the, so here we have this angle, we use angle alpha, not theta. So here we have this angle alpha, and we see that mg is equal to T multiply, like absolute values, T multiply cosines of alpha. And then also we know that this centrifugal force m omega square r is equal, so it's compensated by the horizontal component of tension in the rope, which is T multiply sinus alpha. So we know length of the rope. We don't know this radius, so we need to get rid of this radius later. But maybe first let's express T from first equation. The tension in the rope will be mg divided by cosinus alpha, and substitute it here in the second equation. So then we will get m omega square r equal to mg divided by cosinus alpha multiply sinus alpha. Okay, so here m mass can be cancelled out. Let us now express r, because we don't know r, so we need to express it in terms of L. So it will be L, like the length of the rope, multiply sinus alpha. So you see this is also right angle triangular, so we can express r as a product of hypotenuse multiply the sinus of angle alpha. Okay, now we substituted here for the r instead of r, and we get the following: omega square L sinus alpha equal to G cosinus alpha, and here is sinus alpha. So this sinus can be cancelled out. And finally, we get that cosinus alpha is equal to G divided by omega square L. So this is our final equation. So you see from here that the value of cosine alpha will be larger if we have larger g, like larger acceleration of free falling. So means that larger cosine alpha means that our angle will be smaller. Kind of obvious. If we have heavier or body at the given angular velocity, it will will be tilted from the horizon line at smaller alpha, smaller angle. Then also with longer rope, we see that if we increase length of the rope, it's here in the denominator, we reduce the value for cosine alpha, means that it will be tilted more. And of course, the most influential parameter is omega, like angular velocity. It's in second power, so that's why it's more influential parameters in comparison to G and L in this equation. So the faster we will spin, the proportional to the square of angular velocity, this angle of tilting of the body will be increasing. So this is this kind of class of problems. Let us maybe continue with some other which involve friction and circular motion. Let's go to another slide. And here I would recommend to consider some curved road. Let's have something like this. We have some curved road. We have a car on this road. Not very nice design of this car, but imagine it's a nice car. And it moves with certain linear velocity. So this will be radius of the curvature. And our question, so there is some friction between static friction, because it moves only straight, it doesn't move left or right. So there is some static friction between wheels and the road. So there is some friction coefficient. And we want to know what will be the maximum linear velocity you can drive in this curved road, being not blown away from the road by sliding across the, by getting some sliding between wheels, like tires, and the road surface. So we are looking for some maximum linear velocity. Okay, so probably let's now have another additional drawing next to it to show from different angle, like cross section of this road. So this is our car. And we have some forces which act on this car. First of all, of course, we have weight, and we have reaction of the road. Then we have some of this centrifugal force which tries to pull our car away from the road, and this will be mv squared divided by r. So it's again the same radial acceleration, which is omega squared multiply r, and this is equal to v squared divided by r. It just depends how we which kind of velocity, angular or linear, we are using. So in this particular case, we are using linear velocity since it's more applicable to the case of a car. And
Is this force points towards the center or not? Or
this
is
force is opposite from the center.
Okay, thank you.
Yeah, because acceleration, like radial acceleration, is directed towards the center. So this force is opposite direction from the center. And here we have friction, like this static friction, which keeps our car on its way, so it doesn't allow our car to slide over the road and hit some edges of the road. So now we want to know what will be the maximum velocity, and obviously that we need to be in this condition when so it will start sliding when mv squared divided by r will be equal to the maximum value of static friction force, which is mu s multiply n. So here we take into account that n is equal to mg in this case, and that's why we have mv squared divided by r equal to mu s mg. So we we cancel out m, and then we get v. So again, we should put here maximum square equal to r mu s g, and the maximum is equal to square root. Let's rearrange a bit this g mu s r. Yeah, so this is the answer. So this our maximum velocity will be defined only by three parameters, which is g, like the acceleration of free fall, or you can call it also strength of gravitational field, but that is on Earth kind of a constant parameter on the surface of the Earth. And then we have two parameters which can be varied. So first of all, friction, need to have good tires. And second is the radius. The smaller radius of the curvature, the lower maximum velocity. Otherwise, this centrifugal force will be higher than static friction, and this car will just slide away from the road. So that's why roads should not possess very like curved sections with very small radius. Okay, so however, there is an option to use so-called banked roads when the surface of the road is tilted, and that helps to compensate this centrifugal force. And if you select the right angle of this tilted road, you can, with certain velocity, go through this curvature, like curved part of the road, without having any friction between wheels and the road. So in that case, you can even drive this curved part of the road when it's covered with ice, and there is like very small friction or zero friction in first approximation between wheels and like tires and the road, and you still will stay in this road without going out from the road. So let us maybe as the next example, try to figure out which angle.
Excuse me, Professor.
Yes,
Can you show the previous slide?
sure. Mm-hmm.
Okay, thank you.
Yeah, you're welcome. No problems. So again, we have the same picture. We have some curved road and a car moving on it with some velocity. And let's say here we have a sign. We have some allowed velocity on this curved road. So some recommended velocity cars should follow. They should not go faster than this velocity. So velocity v is given. But in this case, if we look at the cross section, it will look a bit different. So this road will be tilted. And this is, oops. This is our car, like wheels. And let us see what is going on here. So we have some weight, mg. Okay, so this is some angle, let's say theta. Then we have reaction of the road, n. So since we have some radius here, r, in this direction, we will have this centrifugal force, which is mv squared divided by r. And well, maybe it's better to have an axis x parallel to the surface of the road. Yeah, okay, will be tilted. Never mind. Okay, so let's have some axis x here like this. And we have here this centrifugal force, we use linear velocity, mv squared divided by r. And here we have a projection of our weight. So this one, it will be mg multiply sinus theta. So you see why sinus theta, because it's the same as we had it before. Here this angle is theta, so let's clean it a little bit. That's why here we also have this angle theta between the normal direction to the plane and our weight. So that's why we have this end reaction of the road is equal to this projection of weight to the axis y, and it will be mg multiply cosinus theta. So it doesn't move up or down, so these components are cancelled out. We are kind of don't along the axis y, we don't care what is going on, but we are interested what is going along the axis x. So these two forces, mg sinus theta and mv square r, if we want this car to be able to go through this curved part of the road without any friction, so without necessity of friction between the tires and the road surface, these two forces should be equal to each other. Then let's write mg times sinus theta should be equal to mv square divided by r. And now we can determine at which angle theta this road should be tilted to reach this condition if our velocity is given. So we cancel out this m and can get the final equation. Sinus theta is equal to v squared divided by g times r. Okay, so this is our final equation, and let us see what it means, because it's not just algebra in terms of getting some final equation. We need to understand the physics behind it. So let's analyze the equation. We see that, well, g could be considered as a constant, so there are two parameters. R, again, if this radius is smaller, sinus theta will be larger because radius in the denominator. And larger sinus theta means that we need to have larger angle. So in order to compensate this centrifugal force for a smaller radius, we need to tilt this road more. Another, again, most influential parameters is velocity. We have v squared. So the higher velocity proportional to the square of this velocity, sinus theta will increase, and means that it's really important to follow some recommendations on the curved road, because it's not just linear dependence but square dependence. So this will make a really huge difference in the way how your car will behave. So this is the most influential parameter. Velocity is the most influential parameter in this particular example. Okay, this is, I guess, pretty much everything what I wanted to discuss during this class. And I think that after this, we will move forward and discuss, start working on energy, if I'm not mistaken, kinetic and potential energy. Oh, there is a question. Isn't that friction should be directed opposite to velocity? Well, this is, we are considering not friction between spinning wheels and the road. Like, we are considering, so if you consider this car, it moves perpendicular to the plane of the image. but we are interested in the friction which is between wheels and the road in direction which is perpendicular to the velocity, because you want to keep your car going straight along the straight line along the road. So this friction between wheels and the road in perpendicular way to velocity matters for the safety. That's why we consider this friction in, actually we considered this friction in the previous example when we have just flat road, and for sure we need to rely on this friction. But if we tilt the road, we can compensate centrifugal force by horizontal component of mg, in this case along the axis x, and we don't need to rely on friction between wheels and the surface of the road. In this case, when road is banked or tilted, it with certain velocity it can go through this curved part of the road without necessity of friction between wheels and road perpendicular to the direction of motion. It's that direction which we don't want our car move. We want it to move straight, not left and right on the road. Will these topics be covered in the midterm exam? Again, look in the manual. It's mentioned which topics are in the midterm exam, but I believe that midterm exam will be only with units, vectors, or 1- and 2-dimensional motion. I think that dynamics, like laws of motion, most likely they will come to the next midterm exam. But again, double check it in the manual, because there is a number of chapters which are going to be considered for midterm, for each midterm. Yeah. Okay, guys, then thank you very much for attention. We will have this meeting on Thursday, hopefully. I believe that afterwards we'll have some new information to share with you, hopefully, about the plans for future. And see you on Friday during our next class. Have a good.
Thank you.
Thank you.
Goodbye.
Bye.
So have a good day. Bye. Bye-bye.